So let's calculate the rate law order. We could have done this in the previous cases. We did a little more intuitive, hand wavy, even when we were writing some of the equations. But there is a way to calculate the order in a rate law using the data that were given in these tables. You can do this whenever you want. So you could do it to error proof your solution. You could use it for cases where it's not obvious or your brain doesn't immediately recognize that something has been doubled or quadrupled. It will work always. The way that it works is that you'll pick two trials and compare the rates to the concentrations and the exponents. So I guess I've picked generically trial A and trial B, or trial 1 and trial 2. Either way, write the entire rate law for one of them and divide it by the entire rate law for the other. And we're going to do an example. So this is a great example because it has two reactants and we have now data for both of them. Our data tables are getting a little bit bigger. The reaction is NO2 plus CO, making NO and CO2. I have 4 trials. I have my initial concentrations of NO2 of 0.1, 0.2, 0.2, 0.4. For carbon monoxide, it's 0.1, 0.1, 0.2, 0.1. And then I have all of my initial rate values. So I'm looking for what is the dependency on NO2 and what is the dependency on carbon monoxide. So I need 2 trials to compare where one doesn't change and 2 trials to compare where the other doesn't change. So from trial 1 to trial 2, NO2 is 0.1 and then 0.2. Carbon monoxide is 0.1 and 0.1. So if I compare trials 1 and 2, it will tell me how the NO2 concentration change affects the rate because it is the only thing changing. It doesn't matter what goes in the numerator and what goes in the denominator. I've chosen to do trial 2 over trial 1. You could do 1 over 2. So for trial 2, my rate is 0.0082 molarity per second, and that is equal to the rate constant times 0.2 molar to the m power times 0.1 molar to the n power. All divided by trial 1, where the rate is 0.0021 molarity per second, and that is equal to the rate constant times 0.1 molar to the m power times 0.1 molar to the n power. So in this whole thing, we haven't found the rate constant, but it's the same for both trials. So the temperature is going to be the thing that affects our rate constant when all other things are the same. So it's the same for both of these trials. We'll cancel it out. And then we don't know what n is, but 0.1 to the n power divided by 0.1 to the n power is 1. So those two things will cancel out. And what I'm left with, if I divide the rates, I get 3.9. And on the right side, I have 0.2 to the m divided by 0.1 to the m. I can combine these so that it's 0.2 divided by 0.1, that whole thing to the m power. 0.2 divided by 0.1 is 2. So especially if I take my 3.9 and I just round it up to a 4, 4 equals 2 to the m power. This can only be true when m equals 2. So I kind of did the last piece there by inspection. If you get something where it's not easy to do this last step by inspection, you can do something like take the log of both sides and manipulate it, use the algebra that you know to get the m out of the exponent so that you can solve for it. Let's do the carbon monoxide change, which We might be able to do this one by inspection. We'll set it up mathematically either way. So trials 2 and 3, my NO2 stays the same, my CO changes, and my rate doesn't change. So you can, without doing the math part, I changed the concentration of carbon monoxide. My rate did not change, so there's no dependence on the concentration of carbon monoxide in the rate of this reaction, according to the rate law. However, we can also set this up mathematically. If we do trial 3 over trial 2, I have the rate K 0.2 to the second power. I mean, or we could write M, but we know that it's a 2 because we already solved for it, times 0.2 to the n power, and then trial 2 on the bottom, rate K 0.2 to the second power and 0.1 to the n power. So canceling K and canceling 0.2 squared, my rates are the same. So I have 1 on the left-hand side. On the right-hand side, I have 0.2 to the n divided by 0.1 to the n. So 0.2 divided by 0.1, both to the n power. 1 equals 2 to the n power. This can only be true when n is 0. Since anything to the 0 power gives you 1, this works mathematically, and you can mix and match, right? You could have done M mathematically, N by inspection, and that would have been totally fine. I just wanted to show you for both of them what it looks like. So this means the rate is equal to K NO2 squared times CO to the 0 power, but right, that's just 1. We're going to leave it off. So your rate law would be the rate is equal to K times the concentration of NO2 squared. We now have enough information to find the rate constant. So if I have not asked you to find the rate constant, but I ask you for the rate law, you would write where we've ended right now, which is the rate equals K times NO2 squared. If I ask you to find the rate constant first, then you're going to need to report it in your rate law. So let's talk about how to find it. If we were doing a slightly better job of being perfectly scientifically appropriate, we would do this for every trial. We take an average, we do some statistics. We're not going to be that good at people. We're just going to pick any trial, get the rate constant in there, try to get some meaningful information about it, but accept that we're not doing kinetics research, so it's okay. So for any trial, you will know the rate and you will know the concentrations. So the rate constant is the rate divided by, in this case, NO2 squared, but in every other case, divided by whatever those concentrations and dependencies are. So for this reaction with the trial I've picked, the rate is 0.0021 molarity per second. I'm dividing it by 0.1 molar squared. So I get 0.21 numerically. When I cancel out these units, I get 1 over molarity times seconds, which is so weird. But units on the rate constant are vital to having the rate expressed appropriately. So the rate is always in molarity per second, no matter what. And unlike the equilibrium constant, we're not canceling out units before we put our concentrations in. So the concentrations go in units of molarity. The rate is always molarity per second. The purpose of the units on the rate constant are to bridge the gap between those two. So for 0 order, my rate is in molarity per second. My concentration is non-existent. So the units on my rate constant are molarity per second. For first order, the units of my rate constant are 1 over seconds because I have units of molarity. I have nothing that would contribute per second, so my rate constant does. Now, you You could memorize what these units are. I don't recommend it. I recommend knowing that the rate is always molarity per second and then figuring out what the units are based on whatever concentrations and orders you're putting in.